So the title is Homomorphisms from Finite Subgroups of SU2 to Langlands Pairs of Groups. And this is based on a collaboration with my student Yuki Kojima and our postdoc Sunjin Choi. And the math part of the paper is already available on the archive, and we are preparing the physics part of the paper. So I was told by the organizer that this is for a mixed audience of string theorists and mathematicians. So I'm going to try to appeal to both. I'm not sure how successful I will be, but let me try anyway. So since 1980s, many new mathematical conjectures have arisen from the study of string theory and or supersymmetric QFTs, as you might know already. And the two most famous examples are mirror symmetry of Calabi-Yau manifolds and the Seiberg-Witten theory of four-dimensional manifolds about differential structures on them. And the mirror symmetry of Calabi-Yau manifolds came from two-dimensional supersymmetric QFT in the context of world-cheese theories in string theory. And Seiberg-Witten theory of four-dimensional manifolds in turn came from the study of four-dimensional supersymmetric QFT. And the topic there is also called Seiberg-Witten theory on the physics side, but the content of the math part of Seiberg-Witten theory and the physics part of the Seiberg-Witten theory are rather different, but eventually they are based on the same ideas. And as you know, Seiberg-Witten theory on the math side has had a profound impact on our understanding of differential geometry of four-dimensional manifolds. So today I'm going to discuss a new mathematical conjecture, which we recently found from the properties of, again, four-dimensional supersymmetric QFTs. And honestly speaking, it seems much, much shallower than the two examples I mentioned, mirror symmetry or Seiberg-Witten theory. But this shallowness gives us different merit in that this is such a simple case of how such a new mathematical conjecture can arise from physics considerations. So I think this can be used as a toy model for this kind of interaction between physics and mathematics. So that's the idea. So the rest of my talk is divided into three parts. One is the conjecture. So I will just present the conjecture so that all of you will be able to understand. And then I'm going to discuss physics derivation, quote unquote. So that will be sufficient for physics audience, but that wouldn't be considered as a proof at any level by mathematicians. But I'd like to give you the idea of how such a relation could be, quote unquote, derived from physics considerations. And then finally, although this conjecture has not been proved yet, I mean, it's just us, three of us, so surely we couldn't, there's no question that so far we couldn't prove it, but it doesn't seem to be too deep, so we could already prove some subcases, and in view of time, I will only give proof of one particular subcase of this conjecture. So that's the plan of my talk. So let me proceed. And if you have any questions, please do interrupt me. Yeah. So the conjecture. So what's the conjecture? So let me start with very general definitions. So let gamma and G to be groups, and let hom gamma G to be the set of homomorphisms, all homomorphisms, right? And then let me denote by rep gamma G to be this set of homomorphisms under certain equivalence relation, where two homomorphisms are declared to be equivalent when there is a group element G on the target side, not on the source side, such that the conjugation by G of this one homomorphism is equal to the other homomorphism for all gamma in capital gamma. So it just means that we identify two homomorphisms when they are related by inner conjugation by the target group G. So the reason that I chose this notation was that when G happens to be UN, then this is just a set of isomorphism classes of n-dimensional complex representations of gamma. And we physicists often confuse isomorphism classes of representations and representations themselves. So hence the notation. Some of the mathematically oriented members of the audience would object by saying that you should always distinguish isomorphism classes of representations and representations. But for the rest of the talk, I will just say representations whenever I mean isomorphism classes of representations. So please forgive me about that slight abuse of the language. Then I need to specify what are gammas and what are G's. So gammas are chosen from finite subgroups of SU2. And G's are actually chosen from Langlands dual pairs of compact simple Lie groups. So let me discuss them in turn. So gamma, as I said, is a finite subgroup of SU2. And there's a well-known classification. So they are either Zn, which is a cyclic group of n elements in SU2 generated by this diagonal matrix, or, well, we can adjoin an element 0, -1, 1, 0 to this cyclic group if the order of the cyclic group is even, and then you get a subgroup, which is called binary dihedral group with 4n elements. So that's another class of subgroups. And then there are three exceptions. They are called binary tetrahedral and binary octahedral and binary icosahedral groups, T hat, O hat, and I hat, which are the pre-images under this standard 2-to-1 projection from SU2 to SO3 of the symmetry groups of the tetrahedron or octahedron or icosahedron. So these exhaust the finite subgroups of SU2, and famously they follow the ADE classification. So Zn corresponds to an-1. Confusingly, D hat 4n corresponds to Dn plus 2, and T hat is the E6, O hat is the E7, and I hat is the E8. So this is the very basic part of the Mackay correspondence. And I'll come back to this correspondence later if I have time. So that's the gamma part. Let me move on to the G and G tilde part. So let G be a compact simple Lie group, and then G twiddle to be its Langlands dual. This concept of the Langlands duality appear both in number theory and also in the study of four-dimensional supersymmetric QFT. And on the numbers theory side, I don't know anything, but people say that it was introduced by Langlands in his Langlands program. I know a bit about the side for the QFT, and they arise as part of the S-duality of supersymmetric gauge theory, which is a generalization of the electromagnetic duality of the Maxwell theory, as I'm going to review later in this talk. So the defining properties of a Langlands dual pair of groups are the following. So there are two ingredients. One is that the Dynkin diagrams of G and G twiddle have arrows reversed from each other. So that's one, but this only determines the Lie algebra part. Then you need to specify, in order to specify exactly which group we are talking about, we demand that pi1, the fundamental group of G, is equal to the center of the G twiddle, and vice versa. I mean, center of G is pi1 of G twiddle. So these are the two conditions. And these two conditions are known to determine G twiddle up to isomorphism from G and the other way around. So that was a bit abstract. So let me give you examples. So one example is to take G and G twiddle to be SUN. So the thinking diagram is like this. Then G to be SUN and G twiddle to be SUN over ZN or PSUN or PUN. Everything is the same. So let's check that the second condition is satisfied. I mean, the first condition is automatically satisfied because this is simply laced. There are no arrows. So its thinking diagram is preserved under the duality. And a center of SUN is Zn, while a pi1 of SUN over Zn is Zn because you divided the simply connected space by freely acting Zn. So this Zn is the pi1. On the contrary, a pi1 of G, I mean, SUN is trivial because it's a simply connected version, and Z of G twiddle is also trivial because we divide it by the center. So the condition of the Langlands dual pair is satisfied. Another example is to take G to be SO2n plus 1, whose thinking diagram is like this. So there's a single arrow pointing towards the last point. And I will take G twiddle to be SPN, whose thinking diagram is this. So the arrow direction is reversed. So one choice of the group structure is to take G to be SO2n plus 1 and G twiddle to be SPN. So if you do that, ZG, I mean the center of SO odd is 1 and pi1 of SPN is also trivial. So this is satisfied. Pi1 of G is Z2, as is well known, and the center of SPN is Z2. So they satisfy the conditions. Or you can take G to be spin 2n plus 1. In that case, the center is Z2. So to match that, you need to quotient SPN by Z2 so that pi1 of G twiddle is Z2, right? So this condition is satisfied. On the contrary, pi1 of G is now trivial, and Z G twiddle is also trivial. So this also satisfies the conditions of the Langlands dual pair. So examples of pairs of G and G twiddle include SUN, comma SUN over ZN, or SO2n plus 1 and SPN, and spin n plus 1 and SPN over Z2. So there are many other choices, but these are the examples we actually treated in the paper. So that's why I introduced them, but they give representative examples, right? So it can happen that the thinking diagram doesn't change, like in this first example, but the global form of the group are different. And there are also cases where the thinking diagrams or Lie algebras themselves are different. But even in those cases, there are multiple choices of the pair. So now we have introduced all the protagonists to state the conjecture. So that's this. So our conjecture is that for a finite subgroup gamma of SU2 and a Langlands dual pair G comma G twiddle of compact simple Lie groups, the size of this rep gamma G is equal to the size of rep gamma G twiddle, where rep gamma G is the set of homomorphisms from gamma to G up to conjugation by G. So it's just, our conjecture is just that the number of homomorphisms up to conjugation by G is the same when you replace G and it's Langlands dual. So that's our conjecture. So before going further, let me make a remark. So although, I mean, these two sets are finite, right? But, and I claim that, I mean, our conjecture says that these finite sets have the same number of elements. Therefore, of course, there are many one-to-one bijections, right? But we don't think that there is a natural one-to-one map. Rather, the situations we expect and we actually see during the proof of one subcase is that there are two vector spaces, V gamma G, with bases labeled by these representations or homomorphisms. Similarly, there's a vector space V gamma G twiddle with bases labeled by the representation from gamma to G twiddle. And because the number of basis elements are the same, the vector spaces have the same dimension, but and there is a natural linear map between the two. But that's non-trivial. If you represent the map in terms of a matrix between two bases given by this and that. So that's the kind of the situation. So we seem to have something similar to discrete Fourier transformation or something like that. So let me, again, before going further, let me tell you the status of this simple looking conjecture. So while we are preparing a math paper, we were surprised to find that actually this case of gamma being the cyclic group and GG twiddle arbitrary was already proved in a math paper written in 1985. I have zero idea why this Croatian mathematician got interested in this question, but well, that's what it is. It was proved, and at least our conjecture is consistent with it. But he did not consider a generalization to make gamma to be a other finite group or finite subgroups of SU2. And then our mathematical contribution is, well, we formulated the conjecture, but then we proved this subcase where gamma is arbitrary and G twiddle is SUN and SUN over Zn. And we proved it using Mackay correspondence in a nice and conceptual way. We also treated this case when gamma arbitrary and SO2n plus 1 and SPn in a similar manner, but less conceptually. And we also treated just one case of spin 2n plus 1 and sp2n over Z2. And that computation is really complicated, but well, we just wanted to make sure that things work, even in those non-generic cases. So that's the mathematical status as far as we know. Maybe some of you know that there are previous works, but that's that. There are also some related mathematical works we found while writing up the paper by looking over the previous literature. So although people haven't phrased or not, people were not interested in the equality of the number of elements, people were interested in actually determining this representation, set of representations from polyhedral groups, I mean subgroups of SU2 or SO3 to various exceptional groups. So for example, if the target group is E8, Darin Frey wrote memoirs of AMS determining all of these representations from alternating group of 5 elements or SL2Z to SL25. So this is the icosahedral group, and this is its double cover. So this is exactly the type of groups we are interested in this conjecture. And again, I have zero idea why this mathematician got interested, but this work caught the eyes of two very famous mathematicians, one Jean-Pierre Serre and then G. Lustig, who determined rep alto 5 G, but not SL2Z5. So for our purposes, I mean, from our physics perspective, it's more natural to consider the map from binary icosahedral group, not icosahedral group. But these gentlemen determine the homomorphisms from the non-binary icosahedral group. So I presume that their methods can be applied to the binary icosahedral groups, but I haven't done that yet. Again, I have zero idea why Jean-Pierre Serre or Lustig got interested, and also I know very well that the fact that the famous mathematicians got interested does not imply the importance of the problem. But anyway, I just wanted to mention that these set of homomorphisms up to conjugation, it's something some mathematicians do care. Right. So I have a request, gentle request to mathematicians in the audience. So please come up with the uniform proof of the conjecture. It seems okay. I mean, we actually have mathematical proofs of some subcases, and we have a uniform physics derivation, which might be good enough for some of you, but not good enough for all of you. And even proving some other subcases would be welcomed. For example, generalizing the old works, the old work, which studied maps from Zn to G comma G12. I think that can be generalized to homomorphism from binary dihedral to arbitrary Langlands dual pair. So that shouldn't be too hard, I think. Well, if you are into group theory. So I hope that some of you or some other mathematicians got interested and then prove the entire conjecture or part of the conjecture. I mean, it's a simple conjecture, right? I mean, you don't have to learn too much about group theory to understand what this conjecture is. So it might be a good pastime for some of you when you are tired of your own current investigation. So you might have some fun thinking about it in your spare time. So I'd like to ask that. All right. So that's the status of the conjecture and the statement of the conjecture in the first place. Was it clear? Okay. So let me go to the physics derivation. So recall the Maxwell equation. Here I wrote it using differential forms and in four-dimensional notation. So F is the curvature of U1 connection. So that's the electromagnetic field strength. And star is the Hodge star. E is the electric coupling. And JE and JM are electric and magnetic current. So this is the standard Maxwell equation in the relativistic form, in the differential form notation. So for simplicity, let's set the currents to be zero. And you clearly see that there's a symmetry exchanging 1 over E squared star F with F. In other words, if you define F twiddle to be 1 over E squared times the Hodge star of F, and on the other hand, if you define 1 over E twiddle squared star F twiddle to be F, then we have the same form of the equation with F twiddle. This is the electromagnetic duality of the Maxwell theory, and it is known to hold quantum mechanically. So exchanging F and star F, if you decompose the 6 components into 3 plus 3, then it becomes an exchange between the 3 components of the electric field and the 3 components of the magnetic field, as you know. So, but one point I wanted to mention specifically is that in this exchange, the electric coupling E becomes the dual electric coupling, and the E twiddle is 1. So when E is big, E twiddle is small, and when E is small, E twiddle is big. So that's that. Maxwell theory is based on U1 connections. Yang-Mills theory is obtained by replacing U1 with non-abelian group G. The equations are very similar. So F is now the field strength or the curvature of a G connection. And then the equations are d of 1 over E squared times star F is 0, and df equals 0, where capital D is the exterior differential operator, including the covariant derivative. And there's a natural question to ask if there is an electromagnetic duality for Yang-Mills. Well, it was found in the 70s by Goddard, Newton, Olive, and Monton and Olive that the W bosons, or electric excitations of Yang-Mills theory, have charges controlled by root vectors of G, while magnetic monopoles, magnetic excitations, have charges controlled by weight vectors of G, where G is the Lie algebra of the gauge group. And if you take the Langlands dual from G to G twiddle, as I said, arrows are reversed, which exchanges weight lattice and the root lattice. The electromagnetic dual of G Yang-Mills, if present, should be a G twiddle Yang-Mills. So that was clear in the late 70s, but it soon became apparent that it didn't work. I mean, the electromagnetic duality doesn't work in vanilla Yang-Mills. Soon afterwards, after a couple of years, people realized that if the electromagnetic duality in the non-abelian Yang-Mills theory should ever work, you need to consider the n equals 4 supersymmetric version of the same theory. So that was pointed out by Olive and Witten and Osborne. But people really didn't believe it, that the Yang-Mills theory, super Yang-Mills with group G and super Yang-Mills with group G twiddle are equivalent. So that's kind of surprising from modern point of view, but that was recounted in an interview of Witten, people in IPMU did in 2014. So if you download these slides and click it, this will lead to the Witten's interview where he recounted how he felt about this whole issue of non-abelian electromagnetic duality. And so people didn't believe it. But things changed in the 1994. And again, decades have passed since then. And there are tons of evidence that it actually works. So the statement is that n equals 4 super Yang-Mills with gauge algebra G at coupling constant E is the same as n equals 4 super Yang-Mills with gauge algebra G twiddle and the coupling constant reversed. So I told you what are the Lie algebra G and G twiddle, but how about the choice of groups G and G twiddle? So in the last 10 years or so, we have obtained a much better understanding of the topological properties of quantum field theories in general. And we now know that G Yang-Mills theory has something called one-form symmetries, and the electric one-form symmetry is given by the center of G, and the magnetic one-form symmetry is given by pi1 of G, or I should say Pontryagin dual of pi1 of G. So, and as I said, electromagnetic duality needs to exchange electric thing and magnetic things, right? So the electromagnetic duality should then not only exchange the Dynkin diagrams of G and G twiddle by exchanging the order of the arrows, but also it should exchange the center of G with the pi1 of G twiddle and pi1 of G with the center of G twiddle. So that's exactly the condition for a Langlands dual pair. So our current understanding is n equals 4 super Yang-Mills with gauge group G at coupling constant E is the same as n equals 4 super Yang-Mills with gauge group G twiddle at coupling constant E twiddle, which is an inverse of the original E. Now, the most basic approach to QFT is by a Taylor expansion in E or E twiddle, and this duality is very difficult to see in such a basic approach. To see this, let X, G, E to be a quantity, some physics quantity observable, associated n equals 4 super Yang-Mills with gauge group G at coupling constant E. Then we should have this equality, right, where E twiddle is 1 over E. But typically, in this Taylor expansion computation, we can only get the first few terms in the expansion in E or E twiddle. So if that happens, then checking this equality is hopeless. or using this equality is hopeless. But things do change if X is a quantity protected by supersymmetry so that it is independent of E or E twiddle, right? In that case, xg of E equals xg comma 0 at zero coupling, and it's computable, right? It's the leading term in the Taylor expansion. And similarly, xg twiddle E twiddle is xg twiddle comma 0. That's also the leading term in the Taylor expansion, so it's also computable. We therefore should have the equality that xg comma 0 is xg twiddle comma 0. So this equality was derived, quote unquote, using S duality or electromagnetic duality, which is a very non-trivial identity of supersymmetric QFTs. But the final expressions for xg comma 0 or xg twiddle comma 0 do not usually involve QFTs. It involves usually just the standard well-defined mathematics. Then the equality becomes a well-defined conjecture in mathematics. So let me summarize what we did. So we start from group G and G twiddle, right? And then we construct n equals 4 G super melts and n equals 4 G twiddle super melts. And they are the same as quantum field theories, we claim. And because they are the same, if we compute the quantity X, xg and xg twiddle should be the same. But the issue is that the shaded area here is not mathematically rigorously well defined. So for the point of view of a rigorous mathematician, this looks like this. Physicists like me tell you to compute xg out of G and xg twiddle out of G twiddle for whatever reasons that they don't understand. And these two things should become somehow the same. So that's how the mathematics conjecture arises, from shady areas where things are not well defined. So many other conjectures derived from supersymmetric QFTs follow the same pattern. For example, you might have heard about something called homological mirror symmetry. So that's about 2D supersymmetric QFTs. So what happens is that there is a relation between two supersymmetric 2D QFT called the mirror operation. So QX and QI can be mirror to each other. And in that case, if you compute the category of A branes on one side and category of B branes on the other, these two categories should be the same. And that part is kind of almost obvious from the definition. But then it sometimes happens that QFT QX can be constructed from a Calabi-Yau X, and QFT QY can be constructed from a different Calabi-Yau Y. And it is known that if you go this path, you get something called the Fukaya category. And if you go the other path, you get something called the derived category of coherent sheaves on Y. So if you forget about this shady area, somehow physicists tell you that you should compute Fukaya of X from X. And on the other side, you are supposed to compute derived category of coherent sheaves on Y from Y, and they become somehow the same. So this is much more non-trivial than the conjecture I stated, but the logic, quote unquote, of the quote unquote derivation from physics of the mathematical conjecture equality are basically the same. So that's what I wanted to say. So coming back to our specific discussion, to proceed, we need to pick a protected quantity X. So for today's purpose, there are many protected quantities n equals 4 super melt. So when applied to this Langlands dual pair, you get lots of different mathematical equalities and conjectures. But for today's purpose, I just choose a very simple one. So let's put n equals 4 super melts on length space S3 over gamma, where gamma is SU2. So SU2 acts on two-dimensional complex plane, which is basically four-dimensional real space. So there is a unit sphere, which is a three-sphere, S3. Therefore, gamma naturally acts on S3. So you can take the quotient. Now you have a space, three-dimensional space, and if you put four-dimensional theory on it, you have a Hilbert space of states that's infinite dimensional and hard to analyze. So you just take the subspace of lowest energy states. So that's V gamma G. And then we are interested in the written index of that, which is just a trace in this finite dimensional vector space of -1 to the f, where f is the fermion number. So for the mathematicians in the audience, you can just think that in the supersymmetric setting, every Hilbert space is actually a super Hilbert space with Z2 grading, and you just take the trace of that grading operator. For string theorists in the audience, it's just the coefficient of q to the 0 term of the super conformal index of the n equals 4 supermels on the length space divided by gamma. So we compute this x gamma g in the limit where the coupling constant is 0. So it's a weakly coupled computation. It's easy. So as I said, this is basically the graded dimension of the lowest energy state. So we need to identify the lowest energy state. So a configuration, gauge configuration with non-zero field strength has classical energy, which is f squared. And I should have written e squared plus b squared. But in any case, it sets e and b to be 0. So a necessary condition for gauge configuration to be 0 energy, lowest energy, is that f is 0. So it corresponds to flat G bundles on S3 over gamma. And the flat G bundles on a space S3 over gamma is almost by definition corresponds to homomorphisms from gamma to G, pi 1 to G, up to conjugation by the gauge group G, right? That's how the homomorphism from gamma to G up to conjugation arises in this consideration. So this is a necessary condition. But the important point is that this is not a sufficient condition because we just analyzed just the gauge field part. There are many other fields, and quantum fluctuation can give rise to non-zero zero-point energy, even in the supersymmetric case, on a curved manifold, and that's known as supersymmetric Casimir energy. So it's in general non-zero. And you can similarly put less supersymmetric theories on S3 over gamma. And in those cases, this supersymmetric Casimir energy is generically non-zero and positive and depends on particular homomorphisms. So because of that, we usually think, I shouldn't have said we, I always thought for the last 15 years or so that the lowest energy state in a supersymmetric theory on the length space doesn't contain any non-trivial information. But the things are different in the case of n equals 4 supersymmetry, because this huge number of supersymmetry gives you a huge cancellation between bosonic and fermionic contributions to the supersymmetric Casimir energy. So the supersymmetric Casimir energy is actually 0 for any homomorphisms. So this interesting fact was originally found to be true for some random pairs of gamma and G by former student of Origano, Zhu, in these two nice papers. But it was based on a very complicated case-by-case computations. But now we have a uniform derivation. So that is to appear in a future paper. So assuming that this E is 0, in the case of n equals 4 supermels, each homomorphisms up to conjugation contributes +1 to this graded trace in the lowest energy states. So x gamma g is just, yes. Any questions? Was that fine? Okay, so x gamma g is equal to the size or the number of elements in this representation from gamma to g. So as x gamma g was supposed to be x gamma g twiddle, we conclude that the number of representation gamma g is equal to number of representation from gamma to g twiddle. So that's the physics derivation of the conjecture. Okay, any questions so far? So that's the physics derivation. So let me come back to math. So some of you might be satisfied with that, but let's check how non-trivial it is. All right, so let's have a look at the proof. So let me now explain the proof of a subcase of this conjecture where gamma is arbitrary and G twiddle corresponds to SUN and SUN over Zn. I should say that I already said in the beginning of the talk that the other extreme, when gamma is of type A, a cyclic group, and GG twiddle arbitrary was already proved in 1985. And we also proved some other cases in the recent preprint, but I don't have time to talk about them today. So let me just stick to this particular case. And that proof also isn't very new. I mean, the essential part was known to many people, but it seems that nobody phrased the outcome in this way. So what do we have to do? We'd like to study homomorphism from gamma to SUN and gamma to SUN over Zn, right? But we are more familiar to UN, with UN, rather than with SUN or SUN over Zn, right? So let's relate these homomorphisms to homomorphism to UN, which are genuine, just ordinary representations of gamma. So recall that we learned something called determinant, which sends a unitary matrix to just a complex number of absolute value 1. Then a homomorphism into SUN is such that homomorphism into UN, but if you compose with the determinant, it becomes identity, right? That's a very roundabout way of saying that it's a map to SUN, but this is it. So let's further rephrase it. So let C be the group of one-dimensional representations. So one-dimensional representation is a homomorphism from gamma to U1, and it becomes an abelian group. So if you take two such representations, you take the product either pointwise, or if you prefer, you just take the tensor product, and it's an abelian group. So it's a Pontryagin dual of the abelianization of gamma, if you prefer. And recall also that rep gamma G for us is just a set of homomorphisms, gamma to G, up to conjugation in G. Then composing this determinant map from U1 to UN to U1, we have a map from rep gamma UN to rep gamma U1, which is C, right? So after this rephrasing, we found that rep gamma SUN is the kernel of this determinant map, which is a map from rep gamma UN to C. That's just a rewriting of what we already know. Next, consider a map from gamma to SUN over Zn, right? So this means this is a funny way of saying that F is a projective representation of gamma. And it turns out that for any finite subgroup of SU2, the second group cohomology with U1 coefficient is 0. This means that any projective extension is actually a split extension. So any projective representation lifts to a genuine representation. So any such F comes from a genuine representation to UN. But this F twiddle is not necessarily unique. So what happened is that the two such genuine representations, F and F twiddle prime to UN, can descend to the same projective representation, F gamma to SUN over Zn. So F twiddle and F twiddle prime descend to the same F if and only if when, oh, I forgot the F twiddle here and F twiddle there, but these two representations to UN are related by a multiplication by a complex number, right? And because F twiddle prime and F twiddle are representations, C is also a representation. So C is actually a homomorphism to U1. So in other words, there is an action of this one-dimensional representations to the representation from gamma to UN, given by the tensor product or the pointwise product of the values. Then representation of from gamma to SUN over Zn is given by taking representation of gamma to UN and dividing it by the action of C, right? So this group C, the group of one-dimensional representations of gamma, plays an important role. So rep gamma SUN is the kernel of a map from rep gamma UN to C. And on the other hand, rep gamma SUN over Zn is rep gamma UN divided by C. We wanted to show that these two sets have the same number of elements. So we want to show that these two sets have the same number of elements. So we now first need to understand this rep gamma UN, right? Before relating it to C. This is just a set of isomorphism classes of n-dimensional complex representations of gamma. So if you denote by rho I, the ith irreducible complex representation of gamma, this set is in one-to-one correspondence with the solutions to the decomposition of n into ni times dim rho I summed over I, right? It's just irreducible decomposition. So we need to understand rho i's. Here, Mackay correspondence comes to the rescue. So for each gamma, which is a finite subgroup of SU2, do the following. So let V to be the standard two-dimensional representation coming from the embedding of gamma to SU2 and let SU2 acting on V. So we draw a vertex for each irreducible representation of gamma, and we draw an edge between rho I and rho j if and only if V times rho j contains rho I as an irreducible component. In this manner, you get an extended linking diagram of type ADE. So if you start from the binary tetrahedral group, you get this diagram. So here I wrote the dimensions of the reducible representations in the circles. So this is trivial representation. There are two more one-dimensional representations. And if you tensor the trivial representation by the two-dimensional representation, you get this two-dimensional representation. If you take the tensor power of the two-dimensional representation times the two-dimensional representation, you get four-dimensional now ones, and that decomposes into 1 and 3. So that's how this diagram appears. And it becomes the easy extending in diagram, and the same holds for any other finite subgroups of SU2. So let us denote its AD type by German letter G. Please note that this is not the Lie algebra G of gamma G. Here G is SUN or SUN over Zn. Then these solutions to this equation are known to be in one-to-one correspondence to the set of irreducible integrable representations of affine G Lie algebra at level n. So that's a standard fact in the theory of affine Lie algebras, which you can find in any textbook, like Victor Katz's textbook or the very heavy book of CFT, yellow CFT book. So a rep gamma UN, I mean the set of homomorphism classes from gamma to UN is in one-to-one correspondence with the irreducible representation of affine G algebra at level n. Now, we want to study these two objects, right? So these are obtained by somehow relating rep gamma UN and C. C is the group of one-dimensional representations of gamma. So what's this C on this side? So this side, we have finite group gamma. On this side, we have Mackay correspondence. We used Mackay correspondence to transform the information to the affine Lie algebra of type G. What's this C on this side? So C was the group of one-dimensional representation of gamma. So in the case of E6, you have three one-dimensional representations. So C is Z3. And the Z3 generates this graph automorphism of the linking diagram by the tensor product. So if you multiply this 1' to 2, you get 2'. And if you multiply by 1' further, you get 2 double prime, etc., etc. So by rotating the nodes of the linking diagram, you can lifted to an outer automorphisms of the affine Lie algebra. So this group C naturally acts on the set of representations just by rotating the Dynkin labels. Another appearance of the same group C is the following. So let's denote by A check the Pontryagin dual of the finite abelian group. So it's the dual group. Then in this case, C check is known to agree with the center of the simply connected Lie group of type G. So in this case, in the case of this diagram, this is E6, right? And the center of the simply connected Lie group E6 is known to be Z3. And there's a natural correspondence. So the center of the finite dimensional Lie group E6, of course, naturally acts on the irreducible integrable representation of affine infinite dimensional Lie algebra G by a scalar multiplication. So that gives you a map from this set of irreducible integrable representations to this finite abelian group C. Okay, we are coming to the crux of the argument. So the map determinant, or this should be gamma, I'm afraid. I'm sorry. So rep gamma un to C agrees with this. So the determinant map on the side of the representation theory of the finite group gamma is equal to this natural map in the theory of the affine Lie algebra. Similarly, the C action on representation of gamma to un by tensor product agrees with the C action on the affine Lie algebra side. Now we introduce the vector space Vg hat n, which is a vector space with basis Va, where A is an element in this representation of G hat n. So this is the vector space of affine characters of hat G at level n. This is also the Hilbert space of G Chern-Simons theory at level n on T2. Now, C grading, which is a map from rep G hat comma n to C, gives an action of C check on this vector space. And similarly, the C action on rep G hat n gives a C action on this vector space, whose bases are labeled by this finite set. So if you think a bit, kernel, the size of the kernel of the determinant map from rep Gn to C is equal to the dimension of the vector space V fixed by the C check action. And similarly, the size of the representation G hat comma n divided by the C action is just the dimension of the subspace of V fixed by the C action. So it's just a strange way of writing down the original constraint. So the remaining issue is to understand the C action and the C check action on, sorry, I shouldn't have written dim, but Vg hat n. And that was already understood very carefully in 1990s by two-dimensional CFT theorists. And interestingly, the C action and the C check action are conjugate by the action of the S matrix acting on this space. So as you know, in the theory of affine Lie algebra, you have affine characters, and you can perform the S transformation for the modular parameter tau. And as vector-valued modular forms, they have a particular matrix multiplication S appearing in it. So, and together with T, S and T generates SL2Z. Or if you prefer Chern-Simons theory, G hat at level n gives you a modular tensor category, and as such, there are matrix S and T, and that matrix S acts on this vector space, and this relates the C action and C check action. So it's explained, for example, in section 14.6 of this famous 2D CFT textbook. So because C check action and C action are conjugate by a matrix, invertible matrix, of course the dimension of the fixed subspace is the same. So this means that these two are the same, and we argue that these two are the same, and these two are supposed to be number of representation for gamma to SUN, or numbers of representation from gamma to SUN over Zn, proving this subcase of the conjecture. So that's it. So somehow, interesting thing is that the affine Lie algebra, whose gauge group is determined by the finite group we are quotienting with, appears in the process of the proof. And if you read the original paper by Zhu, physics paper, where this vanishing of the supersymmetric Casimir energy was first noticed, that guy already described the duality chain where he mapped the original n equals 4 super system to this Chern-Simons theory. So it's fairly natural that the same Chern-Simons theory plays some role in the proof. Okay, so I came to the end of the talk. So let me summarize. I described the mathematical conjecture, and I gave you a physics derivation. And then I didn't discuss multiple proofs, but I discussed a proof of one particular subcase. So thank you very much.